CMOS digital cameras dominate the consumer marketplace. This is also true for astrophotography cameras. The day of the CCD has reached its sunset. The manufacturers of consumer cameras have put a lot of time, effort, and software into their cameras, with much of this dealing with how the camera deals with ISO and exposure length. By comparison, astrocams have a minimum of software in them, which puts more responsibility on the astrocam owner to ensure that the images they take can be converted into amazing astrophotos. I'm going to give you a few insights as to how CMOS imaging chips in DSLRs work, and I'm going to generalize a lot because big companies like Canon and Nikon have their own secret sauce which they never make public. CMOS imaging chips manufactured today have significantly more pixels than what is reported by the camera manufacturers. This is because there are a block of pixels on the imaging chip that have been painted with an optically black paint. Consumer cameras, including DSLRs, use these blackened pixels to their advantage. The majority of dedicated astrocams do not use these blackened pixels. Why would you put black paint on those pixels? Whenever a photo is taken, these optically blackened pixels are exposed to the same temperature for the same time and using the same electronics as the rest of the pixels on the chip. The only difference is that no light reaches these blackened pixels. This means that when these pixel values are read, they only contain bias, read noise, and dark current. The DSLR camera manufacturers take advantage of this knowledge by first reading the values from these blackened pixels. They determine what the average blackened pixel value is and use this knowledge to optimize how the A to D conversion should be performed when reading the rest of the pixels on the chip. This ensures that the best possible image is obtained regardless of whether it's a hot summer day or a frigid winter night. The DSLR camera manufacturers go one step further and impose a data standard on their raw files that I call black ADU. The data written to the raw files is biased up or down for the entire image so that the average pixel value they measured from the blackened pixels is always equal to a constant. This constant is called black ADU, and it's meant to indicate what pixel value will always correspond to zero light. For my 14-bit Nikon D5300 DSLR, the black ADU value is 600. For Canon 14-bit cameras, the black ADU value is roughly 2048. 14-bit Pentax K5 black ADU value is 512. So these values are different for different DSLR camera manufacturers. Astrocam manufacturers do not have a black ADU standard. This means that you can't tell what pixel value equals zero light when examining a light frame from an astrocam. For DSLRs, this black ADU standard creates an interesting situation, which is most notable when taking dark frames. Dark frames are photos taken with the lens cap on the camera lens or telescope camera assembly, so dark frames contain zero light. If you examine the data in a 10-second dark frame taken with a DSLR, you will find that the average pixel values will be equal to its black ADU value. If you then take a 10-minute dark frame, your first guess might be that the average pixel values may be larger. If you were performing this test with an astrocam, you'd be correct, but for a DSLR, you would find that the average pixel value for any dark frame always equals the black ADU value. Bias frames are taken the same way as dark frames, but their exposure time is the fastest possible. The average pixel values in any DSLR bias frame will also be the same as a 10-minute dark frame. This is also true for dark flat frames taken with a DSLR. The average pixel values and bias frames for astrocams will be different for different gains and be different than their corresponding dark frames. Astrocams also have an offset parameter which directly changes the average pixel value. So why would you need or bother calibrating your DSLR light frames if every bias, dark, or dark flat contains the same values? Not even changing ISO affects this result. This is one of those moments where the phrase, "the devil is in the details," is very appropriate. This is also the moment where this video ends. All will be revealed in the Master Darks and Bias video. Stay tuned.